Hello, everyone. Welcome back again to another one of Chegg's office hours. So this session is going to be dedicated to linear algebra, and I'm very happy to be here with you all to help you study and prepare for this class. So my name is Joe. I am a fifth-year PhD student here at NYU and New York University, and I've TA'd for many classes, including this undergraduate linear algebra class. So during this next hour, I'm just here to answer any questions you might have. And otherwise, I have a couple pre-prepared questions that we can go through to kick us off. So here's first question to start us off is computing this matrix product. We have a matrix here, 4, 7, 5, 8, and 6, 9, and we want to multiply it with this vector 1, 2, 3. So let's do it. Okay, so how does matrix multiplication work? First, we have that the matrix is a 2 by 3 matrix, and the vector is a 3 by 1 vector. And so this will always come out to a 2 by 1 vector. And okay, if we recall, how do we compute this vector? We're going to take, for the first entry here, we want to match the first entry here and multiply it with the first entry here, and then multiply this 5 with the 2, and then the 6 with 3. So let's do that. We have, here we have 4 times 1 plus 5 times 2 plus 6 times 3. And for the second entry of this 2 by 1 vector, we'll do the same with this second row. So here we have 7 times 1, matching the first entry here with the first entry here. And then we continue. So we have plus 8 times 2 plus 9 times 3. And what do we get? Okay, let's do it. So we have up here we have 4 plus 10 plus 18, and this is 32. So let me just erase that and write it. And then we have 7 plus 16 plus 27, and that gives us 50. Okay, so that's an example of how to do matrix multiplication. So fairly straightforward. We just need to remember this formula. So to get the first row, we're going to take this first row here and multiply it 1 by 1 with the entries here. Now I want to connect this to a topic that you've probably seen before taking linear algebra, and that's the matter of dot products. So here's a kind of a follow-up question. Actually, let me move this up. So let's compute these two dot products, and hopefully they look familiar. So we have the vector 4, 5, 6 dot product with the vector 1, 2, 3, and also the vector 7, 8, 9 dot product with 1, 2, 3. So give you a second so you can do this on your own first. And if you have the answer, then you can also write that in the chat. All right, so let's compute this now. So this dot product, Remember, for doing a dot product of vectors, we just multiply pairwise by the entries. So 4 times 1, 5 times 2, and 6 times 3. But actually, if we see that's actually exactly what we just did up here in the previous question. And so this first dot product is just equal to the answer that we got, 32. And actually the same for the second, right? So the second dot product is exactly the computation we did up here. And this is 50. And anyway, so this is to highlight that doing this matrix multiplication, there's two ways to view it. One we'll see in my next example that I prepared. But one way of the two is to view it as doing a dot product, or a dot product for each row. And so this is an interesting fact from the definition of matrix multiplication, that it's just a dot product, because now it also ties this together with the concept of orthogonality, right? If you remember, what does it mean for two vectors to have a dot product of 0? It means that if you were to draw them, they would be perpendicular to each other, or orthogonal to each other. And so if I wanted to find vectors that are orthogonal to the rows of a matrix here, or perpendicular to the rows of a matrix, then I can actually solve for this matrix times a vector to be equal to 0. And so that's relating this matter of matrix multiplication through dot products to the matter of being perpendicular. And we'll see how that ties together with other concepts of linear algebra in a bit. But I wanted to mention this now because if you're taking linear algebra as a class, this concept of being orthogonal or perpendicular comes up again later in the class. But I wanted to just show you that you actually get some hints of it even from the very beginning of the class. So, okay, before we do the next question, which is also kind of a follow-up question to this matrix multiplication, just pause here and say again to everyone who just dropped in that this is a Linear Algebra Office Hours time. You're welcome to ask any questions on linear algebra, and I'll be very happy to answer them. Just some comments that I'm seeing from TikTok. So there's your favorite sauna. Can you do statics? Well, unfortunately, I cannot in this session. This session is just focused on linear algebra. But, we'll be having these office hours throughout the whole week. Actually, I'm not sure if there's an office hours for Chegg on statics, but you can check the schedule by going to their website. But also, in general, for homework help, you can scan the QR code in the top left to subscribe to Chegg. And I believe right now they're also doing a coupon. So there's a discount if you sign up through, I think there should be a link in the chat that you can see for that as well. Also a TikTok comment from Cade, off topic, but what's your PhD thesis going to be about? Well, I don't know how much I'm allowed to say during this time, but and just really quickly, because obviously I love talking about what I'm doing in my PhD. Well, my specialty is in probability theory at NYU, and I'm working on specifically something that's called the Ising model, or the Potts model. You want to Google that. So anyways, but I don't think I should spend more time about that. Okay, so let's jump into the next question. But of course, feel free to put your own questions in the chat. Actually, it would be really helpful if you're taking the class. You can let me know what you're covering in the class right now, and then that will help me also to give more guided questions to exactly what you're doing. All right. So here's another question. Is the vector 16, 25 in the span of the vectors 4, 7, 5, 8, and 6, 9? So, well, this is a yes or no question, but give you a second to think about it, and then I'll give my answer. Yeah, at Cade from TikTok. That's so cool. Thank you. I also think it's very cool. There's lots of interesting problems in that field of research right now. Okay, so this is a yes or no question, so I'll just give the answer. The answer is yes. But how do we see that from the computation we just did up here? Well, this points us, okay, so actually I'm going to copy down what we solved up here. Advanced orange, is it yes? That is the answer. So in the previous problem, what did we do? We saw that this matrix 4, 4, 7, 5, 8, 6, 9 times the vector 1, 2, 3 is equal to the vector 32, 50. So, all right, sorry about this resizing thing. So we just saw in the first problem, right, that doing this matrix multiplication, one way you can think of it is like doing a dot product. But here's another way. Another way to interpret this is really that it's like taking a combination of the columns here of 4, 7, 5, 8, and 6, 9, weighted with these entries. So what I mean by that is it's like taking 1 times the first vector plus 2 times the second vector plus 3 times the third vector. Oh, it's cut off by the text. Okay. So that means what? That means that whatever I get as the answer here is going to be a combination of the columns of the matrix, specifically it's given by this combination. Right, so this answer, 3250, is just equal to some specific combination of the columns of the matrix, and namely the one given by these weights. So that's also how you should interpret. Actually, I would say this is the main way to interpret matrix multiplication. It's like taking a weighted sum of the columns here. Okay, but what does that mean for this question? Is this vector in the span of these vectors? We see that the answer would just be yes, because we've just computed that 3250, which is twice 1625, is in the span of the vectors. All right, so we can write thus we know that if we were to just have like halve, HALVE, all of these numbers, we would get half the answer, which is then 1625. So we know that 1/2 times 4, 7 plus, I'll just write 2/2 to be clear, times 5, 8 plus 3/2, 6, 9. is equal to 1625. All right, and also I know that there's going to be a lot of definitions getting thrown around for linear algebra, but this is the picture you should have of what a span is, in case that wasn't clear. So this question involved the term, involved this term of span. And okay, so that has a specific definition, but without going into without writing that out, this is what it means. It means that there is some combination of these vectors that once I take like a weighted sum with the right numbers here, then I'll get the vector that I'm asking for to be in the span. So that's how we should think of span as well. All right. So let me pause here before going to the next question. If you've just joined us, welcome. This is a Linear Algebra Office Hours. So my name is Joe, and I'm here to answer all of your linear algebra questions. You can feel free to ask a specific question or just ask a question like, can you go over an example involving blah, blah, blah? And I'll be happy to make one up. And also, if you need more general homework help, you can check the QR code in the top left of the screen or the link in the chat, and that will give you a discount for signing up for Chegg. So it's a promo that they've got going on right now. Alrighty. Well, let me go on to another question. So this one is involving a basis and involving a column space. So let's highlight those two terms. That is not the color I wanted. So here we have a question involving a basis and a column space. So just to summarize, as a refresher in case, the column space is the set of vectors that you get from spanning all of the column vectors here. So column space is the span of the column vectors, these vectors. Whereas a basis is going to be a minimal set in that sense. So it's going to be a set that spans the column space, but also needs to be minimal. And by minimal in linear algebra, we mean linearly independent. So, okay, let's do this problem. So like many problems in linear algebra that I've gone through so far, the first step is to do row reduction. So let's do it. Say 1, 2, 2, 4, 4, 5. This is a row reduced to, remember for row reduction, we want to get rid of this entry here. And do that by, let me write this actually. We do that by taking the second row and subtracting twice the first row. And we get 0, 0, and -3. Okay, which can then be row reduced to 0, 0, 1, and then 1, 2, 0. Okay, so here's how we get the basis for a column space. We're going to look at which columns have a pivot, and then we're going to go back to the original matrix and look at the columns that correspond to these columns. So in this case, it's the first one and the third one. So let me write that down. Look at which columns have pivots. And then we select those columns from the original matrix. Okay. So in this case, we get as our basis, we get 1, 2. So corresponding to the first column, we have this first column here. And then we have 2, 5. Because we have a pivot in the third column, so we're taking the third column from here. Now, okay, just say a common trap when you do these kinds of problems. You need to make sure that you're not taking these two columns, okay? So the answer, as a side note, okay. The answer is not 1, 0, comma, 0, 1. Okay, so that would be if I'm taking the columns with pivots here, and then just taking those two columns as my basis. So that will not get you the right answer. Okay, technically in this case, if you checked, it would actually be the right answer. But in general, it will not be correct. And so you have to make sure you go back to the original matrix. And that should make sense for this reason. Let me explain it like this. So remember that the column space is what? It is the span of all the column vectors. Okay, column space, span of column vectors. And so a basis for it, if you wanted a set of vectors that spans the column space, you can simply start off by just taking all the columns. But the issue is that that might not be minimal. So you always want to just start by taking all the columns. But the point is that some of them might not be linearly independent. So, okay, what's an example is here. You see that the first two columns are linearly dependent, right? They're on the same line. And so this just taking all the columns doesn't get me a basis. It's not minimal in terms of spanning sets. But what this procedure does is it selects a subset of the columns, namely here the first and the third. So for finding a basis of the column space, you should think of it as you're starting with just taking every column, and you want to just pick the correct subset that gets you a linearly independent set. And so that's kind of how you should remember that when you see these pivots, you're not taking these columns, but you're always going back to the original matrix to get the columns. Okay. Let me see. What is my next question, actually? Okay, on the null space. So, yeah, this is a good moment to just take another pause. Do please let me know if you have any topics you want me to go over in this time. Every class kind of goes at a different pace, so I'm just doing my best guess as to where you all are at right now, but you can let me know in the chat what you're currently covering in your linear algebra class, and then I'll be able to give more targeted help. And otherwise, you're always, there's great resource in just going to Chegg itself. And so if you need help with homework, you can, if you sign up with Chegg right now, there's a promo going on. So your first month will be half off. So this is also the time to get help from Chegg. I'll just pause for a moment and give you guys some time to think of any questions you want to ask about either this problem or that you want me to go over. All right, if nothing, let's just dive into the next question. So here's a similar question. We got a concept of a basis again, but this time of the null space. Okay, so so every matrix has a column space and a null space, and although they kind of sound similar, they are pretty different concepts. So let's do this example problem. It's the same matrix as above, and it is the same one, right? Yes. Okay. So we'll do this example, and then we'll kind of compare the similarities and differences. Okay, so the first step again is the same. So we want to row reduce this matrix. Since I've already done it up there, let me just copy that down here. So this row reduces to, what did I write? 1, 2, 0, and 0, 0, 1. All right, so what do we do here? We want to solve, remember the null space is the solutions to ax equals 0. Actually, that's worth writing down. So solutions to ax equals 0. So this is something that perhaps we have seen before. So remember that this corresponds to the equations x, if I call my variables x, y, and z, since there's 3 of them, to x plus 2y equals 0, and to z equals 0. So, okay, how do we do this? My systematic way is I look at the pivots and I will move everything that's not a pivot to the other side. And so here we get x equals minus 2y. And then for any variable that is not a pivot, I'm just going to write y equals y to indicate that it can be anything. And then here I have z equals 0. And now I look at all the variables I have on the right side. So here it's just y. And so here I get x, y, z. Well, actually, okay, I'm wanting a basis. So let me just put these numbers in a vector. Here I have minus 2, 1, and 0. And that's it. I only have one variable on the right side. So this is my basis. Okay. So let's compare and contrast this question with the one above. I see some questions on TikTok. Let me get to them in a second. So, okay, here we start off by doing the same thing. We do the row reduction. We also care about getting the pivots. So that is also what we care about. And so the start of the problem is the same, but what you do after you get the pivots is where it's different. So here we relate this question back to a question like solving ax equals b, in this case ax equals 0. And we get this parametric form of the solution, and this just becomes our single vector in the basis. Another thing to highlight for the differences is that the dimension of the basis is going to be different, right? So here, this is going to be a vector in R3, right? There's 3 coordinates. Oops. There's 3 coordinates. So this lives in R3, whereas the column space, each vector only has 2 entries. So it lives in R2. And okay, why am I saying this? This is just to say that even though the concepts sound similar, null space and column space, they are different things. One of them, they don't even live in the same world, right? This one lives in R2, and this one lives in R3. Okay. Okay. Let me take some time to answer some of these questions. So I guess quickly, can you explain SVD from Reed on TikTok? So SVD, singular value decomposition, is a generalization of diagonalization, is how I would say it. Okay, so since you're asking the question, I assume you know what diagonalizing is. And when you diagonalize a matrix, you get a lot of information, right? You get the eigenvalues and the eigenvectors, and it really decomposes a matrix into what's the key components that's really going on. So you have a rotation aspect, and then a stretching, then a rotation. But the issue is that not every matrix can be diagonalized, right? So you counter, for example, some cases where there's not enough eigenvectors to fully diagonalize the matrix. Another example is when the matrix is just not square. If the matrix, for example, here is a 2x3 matrix, then I can't diagonalize it. So, yeah, but what SVD does is it lets you get the same kind of information. So you get, instead of eigenvalues, you get singular values, but they kind of give you the same, at least on an intuitive level, the same information on the matrix. Kind of describes it gives some measure of the size of the matrix, is one way to think of it. Okay, and so you should think of it like diagonalization is great, but we can't always do it. And so then we do SVD. I guess I could do an example of computing SVD. Maybe you can let me know if you want to see that, but otherwise it will also take a while. But you kind of see that when you do an SVD problem, you're also just kind of diagonalizing twice. So that should also give the feeling that, like, okay, this is like a generalization of diagonalization. And then there's another question from Daddy Jaspel on TikTok. Can you explain? Oh, okay, I see it again. Can you do lower upper factorization and also discuss Cholesky factorization? So, all right, let's do it. Let me go to a new page. There's my mouse. So when I do a lower upper triangular factorization, it means that I'm starting with a matrix A. So, okay, I'm just going to write a random one, 1, 2, 2, 1. And I want to factor it, so write it in matrix multiplication for one where I have a lower matrix, meaning that the only non-zero entries are this one, this one, this one, and an upper matrix, an upper triangular matrix, so one where it's here, here and here. And anyways, what this does is it lets me, well, actually, I guess once you have the lower upper triangular factorization, solving for, as you've written, LUX equals B should be easier. By the way, you should think of lower upper factorization as you should think of it as capturing the information in row reduction. Okay, so let's do an example here. So, well, first of all, you can see that if I want this to be true, I have some constraints. Oh, I guess also I usually want these entries to be ones. Oops. So one way to solve this is to just do it by going through the entries here one by one and seeing what they impose about these starred numbers. Okay, so for example, the fact that this is 1 means that the fact that this is 1 means that this vector multiplied by or dot product with this vector has to equal 1, right? So I get, maybe let me, instead of just writing stars, let me write names for the, what's going on? Names for the variables. All right, this is very weird. Whenever I use the eraser, it's switching to a highlighter. So that was very annoying. But okay, so let's say I have A, B, C, D. Then I can write 1 equals 1 times B. And so, okay, then I solve for B equals 1. So I'll just substitute that in. And now I have, by looking at this entry tells me that 2 is equal to A times 1, which implies that A has to equal 2. And okay, now I can move on to, well, I can plug that in for A. And now I can look at the next one. So this number implies that I need to solve 2 is equal to C plus 0, right? So C times 1. And that implies that C is 2. And okay, lastly, I have that this 1 implies that 1 equals 2 times 2 plus D. And that implies that D is minus 3. Okay. So as you can see, well, okay, it's not obvious why a priori you can kind of solve it very easily like this. But okay, the way that this is set up is such that if you go through the entries here in the right order, and then you just keep substituting the value of the unknowns that you solve for, like I was doing, every time you'll get like a very simple thing to solve, as in it's just one variable. And that's because of the presence of all of these zeros. So you have, because this is a 0, it's going to make the first equation easy. And then once you solve that, the fact that this is a 0 is going to make the next one easy. Okay, well, I gave myself a easy example, right? A 2 by 2 matrix. But you can imagine if you had like a 5 by 5 matrix and you wanted to find a lower upper triangular one, you would still get like a matrix with a ton of zeros. And the point is that this lets you like solve this factorization easily. Yeah, hopefully I didn't make any mistakes. But okay, if this is one way to do it, I don't know if I should say this is the better way to do it, but this is kind of like a turn your brain off and do it kind of way. So I like this way better. But this also doesn't capture the essence of what lower upper triangular factorization is meant for. Lower upper triangular factorization is really meant on a theoretical level to capture what is going on in row reduction. So let me see if I can illustrate that. I'll be honest with you, it's been a little bit since I've seen it, so hopefully I can do this. Let's just look at this. Okay, so this is way number 1, solution 1. And here's another way to do it. Let's just do row reduction for this matrix. Oh, let me move it up so it's not blocked. Okay, well, what is the matrix? Okay, 1, 2, 2, 1. If I were to do row reduction here, I would get, okay, I would take the second row and subtract twice the first one. And I would get 0 minus 3. All right. Okay, I picked a not very informative example, but here's the pattern. Once you do a row reduction, you're going to end up with something that's upper triangular, right? Okay, that's just kind of my definition of row reduction. And it just turns out that when you keep track of the actual row reduction steps, okay, the reason I say this is not very informative is because here there's only one step. But if you tried this with a bigger matrix, say like a 3 by 3 matrix, you would see this. This information gets captured in this lower triangular matrix in the way that you take this minus 2. So this is you took the second row and you subtracted twice the first one. That means when you look at the second row here and the first entry, you get minus whatever this number is. So here is a -2 and here is a 2. Okay, so that's really the essence of lower upper triangular factorization. Is this lower matrix reveals all the information that you had to do when you did the row reduction in the way that this -2 corresponds to a 2 here. And then this, whatever matrix you get at the end, is the upper triangular matrix. Okay, so hopefully that helped. I do realize in hindsight doing this with a 2 by 2 matrix, good for me, maybe not as informative of some concepts for you, but it does generalize like this, and you can try with writing out like a 3x3 matrix or something. So, oh, this is okay, from Daddy Jaspel. This is from my numerical analysis class. Interesting. Yeah, numerical analysis should have lots of linear algebra to it, because it's about approximations, and when you approximate things, you end up with linear equations. But also, there's lots of I guess interesting things to think about when you consider doing computations with matrices in a computationally effective way. Like, how can we multiply matrices in a way that is not too computationally heavy? So it's very cool how linear algebra ties to different classes. Okay. We are kind of running out of time. I did want to go through, let's see. Well, okay, I did want to go through at least this other question, because I think it's informative of a pretty important concept. Yeah. Well, okay. So at Jagraj Gill from YouTube, can you discuss Cholesky factorization? Maybe this time I will not do that. I want to fit in this problem. And also, to be honest, I need a refresher myself. It's been a while since I've seen that. So, but I can try and prepare a question on that for next time. So I'll be here every week, Monday, 7 p.m. to 8 p.m. if you're on Eastern time. I guess, what is that? 4 p.m. to 5 p.m. if you're on Pacific time. So I won't do it this week. Apologies, but I can try and do a question like that next week. Okay. All right. I guess before I dive into this, you can also, I should shout out that if you need help in general with homework, there's you can always check out Chegg's other resources, and they're doing a promotion right now. So if you sign up right now, you get half off the first month. Oh, from at Michael PN from TikTok, favorite matrix factorization. Mine is SVD. Yeah, that would probably be mine too. It just captures so much information on a matrix. Also, I have a very biased perspective in that my focus is in probability theory, and so there the tie to linear algebra is random matrices, and lots of interesting questions there are on the distribution of the singular values. So that's anyways. Okay, let's get into this last question before time runs out. So find all solutions to the matrix equation AX equals B, where A is this matrix and B is this vector. So, okay. What I wanted to say for this is there's two ways to do the problem. So one way is, can you do lower upper triangular on this question? So from Daddy Jaspel on TikTok. No, so lower upper triangular, as far as I'm aware, is only for square matrices. Is that true, actually? Well, I hope it's true. Okay, as far as I'm aware, it is supposed to be for square matrices. But now that I say that, I'm slightly hesitant. I would want to check if that's true. But at least when I learned it, it was only in the context of square matrices, which would not have it apply. Okay, I am getting a little scared about whether that's, maybe there is something you can do, but then I'm not aware of it. Okay. Okay, but at least for sure, if this was a square matrix, say like cross out this first column, then yeah, you could definitely do it. Okay. So, okay, to do these problems, you always have the row reduction. And a long time ago now, I did that up here. 1, 2, 0, 0, 0, 1. And so we have that a basis for the null space for when b is 0 is this vector, minus 2, 1, 0. Minus 2, 1, 0. So that's what we did up there. It turns out, so the solutions, right, were just a number times this vector. Turns out to, so that, let's see, this solves ax equals 0, 0. It turns out to get a vector b that's not 0 here, I can add my solutions here to one specific solution of ax equals b. So why is that helpful? That's helpful because, well, first of all, it illustrates geometrically what's going on, which I'll try and draw out in a second. But it's a lot easier to find one specific solution to ax equals b. Let me see. One specific solution to ax equals b is, does anyone have an answer to this? Okay, let me do it before we run out of time. Here's a vector 4, 0, 0. Do you see why this is true? Remember that when I write a times x, one way to interpret it is I'm taking a combination of these columns with the weights 4, 0, 0. So when I write 4 times the first vector plus 0 times the second plus 0 times the third, I just get 4 times the first vector, which is 4 times 8. So anyways, the point is that I can get a specific solution sometimes without really trying very hard. And the full solution, so the full solution or the solution set to ax equals b is then the solution set to ax equals 0. So c times minus 2, I'll write a little bigger. C times minus 2, 1, 0 plus my answer here, plus one specific solution. Okay, so that's an alternative way to solve ax equals b. Why did I want to highlight this? It's because it shows the relationship between the solutions to ax equals b and ax equals 0. And this is pretty special. The solution to, the solution to ax equals 0 is this line. Let's
let's see if this is x, y, z. It's -2, 1, 0. So it's this line. Okay, well, actually, this whole line, right? And now what is the solution set to ax equals b? It's this line, but it's shifted by the vector 4, 0, 0. So the vector 4, 0, 0 is right here. And I get this green line is the solutions to ax equals b. Okay, so anyways, I thought that was nice to highlight. I think you should see this, that at least once, that in linear algebra in specific, because of this linearity of everything that's going on, if I want the solutions to ax equals b, it's just going to be a shift of the solutions to ax equals 0. You know, to emphasize, this is unique to linear algebra, right? If I want the solution set to, some quadratic equation or something, some trigonometric equation, I can't just solve it for, say, like f of x equals 10 by taking f of x equals 0 and then like shifting it. It doesn't work like that. So this is a special thing to linear algebra. All right, well, we can conclude here. We're basically out of time. And, just to pitch again, there's going to be all these office hours going on throughout the week for other classes. So if you need help with calculus, I know they're doing that. All right, to be honest, I don't know the full schedule, but hopefully whatever class you need help with, you can find on the schedule for these office hours throughout the week. Otherwise, I'll be here every Monday at 7 p.m. Eastern time. And if you need more resources, you can make an account with Chegg. They're doing a promotion right now. So you get half off your first month if you sign up with the promo code that's been posted in the chat. Okay, I see that they also just posted the schedule for the office hours. That's right. There's a YouTube community page. You can check in there. Anything else I want to say? Yeah, well, I don't know. Well, hopefully you guys found this helpful. Anyways, I'll be here every week, and you can come with questions. I'll be happy to do my best and answer them. Just here to help you all do well in your classes. So I'll be all for today. Thank you all for coming, and hope to see you next week.